You guys have probably all at least seen once the example of like a dice problem. Like if I have a fair six-sided dice, how many? So what's the probability of getting any pick number? If you guys is seen this problem somewhere? Okay. So I have my. Make sure I'm seeing the screen. If I have my die, so, and these are not the correct numbers at all. I don't think any of them are mutually exclusive, but anyhow. So I have my dice. If I roll it, I have say I want to know the chance of me getting a 4, right? How would I how would I figure that out?
The number of possibilities versus the remaining possibilities.
Okay, so the number, so I might say the number of desired outcomes, you say, the number of desired possibilities, which in this case, there's only one 4 on this die, so that'd be 1, versus the divided by the total number of outcomes.
And that is equal to what? Probability?
Yeah, so that would be equal to the probability of the desired outcome. So in this case, say that I want to roll a 4. So number of desired outcomes is how many?
1.
Right? Total number of outcomes
6.
means that probability of the desired outcome, bless you,
Thank you.
is what? Or if we wanted to look at it from like a percentage point of view,
Like 17.
it'd be like 16.7%. Which means if you're looking at it from a percentage kind of view, that means that if I roll that die 100 times, just for your volume line. If I roll that die 100 times, about 16 or 17 of those times I should get a 4. All right, so it's relatively straightforward. Now say that I have 2 die. I'm not going to draw the full picture for each because it would take too long. And I have pretty flat dice anyhow. So now I have 2 dice. Okay. Now each one of them, if I want to get a 4 on each of them, it's the same probability, right? So I want to get a 4. Probability that is 1/6, and that's true. That's true for either of them. However, maybe I want to say, what's the probability of getting a 4 on both of them? To do that, take the probability of the event in each scenario and just multiply it together. Does it make sense that this probability is smaller?
Yes.
Okay, I heard both. Why? Whoever wants to start, I don't really care. Just
Were you talking about the probability of rolling just 1 4?
rolling a 4 on both die.
Oh, yeah, then yeah, it makes sense.
Cool.
I thought you meant like just.
Nope. Okay, so it makes sense. So if you want to find the relationship of 2 events, them both occurring at the same time, all you have to do is multiply the probability of each event occurring independently. Now, what's a problem with this? if we want to try to extrapolate this beyond just dice, if we want to say, okay, I've done what's called what's an example? I've thrown a well log down this hole. I have an idea of the porosity of rock at different parts of it. Throw the well log down a bunch more holes. I found a bunch more porosities. I know that that if I look at a particular formation, 20% of it has porosity of over 0.2 in 6 wells, and it's less than 10% in the other wells. So I can start to combine these probabilities now, right? I can say what's the chance of having a porosity greater than 0.2 in the majority of formation in all of these wells. Does that make sense? So if let me try to say it in a less complicated way. So say that I have a bunch of test wells. I find that porosity is greater than 0.2 here for a particular formation. I'm kind of following that for formation across, greater than 0.2, less than 0.2, greater than 0.2, greater than 0.2 for, greater than 0.2. And here it's for 50% of the formation, here it's for 30% of the formation, here it's for 60% of the formation, 65% of the formation here, 62% of the formation there. I can start combining these and say, what's the probability of putting a well into any one of these and getting into all these and hitting a point in the formation and where the porosity is greater than 0.2. Would finding that make sense?
No.
Okay, tell me why.
Most the largest variable would definitely be the depth or the type of rock formation.
Okay. So this is good. This is more what I want to discuss. So all these probabilities that we're doing, this, and pretty much all statistical analysis, probability analysis is very, very much limited, by whatever your input data is, and in a sense by physics. So I can throw together a probability of hitting that porosity sweet spot in all these wells simultaneously. I can generate a number for that. I can take all these probabilities, multiply them together, and say this is my probability of hitting a spot in this formation in all these wells at one time. If I try to drill a lateral that kind of follows along through this entire formation, I can come up with a number describing that. However, it's not physics. That number has no real connection to what's actually down there. It's a good way to estimate things when you don't know a whole lot. It can give you some ideas of what's down there when you haven't had it well characterized. But ultimately, like Ian's saying, porosity doesn't depend on in statistics. It depends on lithology depends on measurable things that actually exist. So a major caution about using a probabilistic approach is that it only goes so far, and it's only as good as its data. If I have, if all I have are these five data points that are somewhat vague, that's not going to hold up very far. So probability is limited by data and by the fact that it's not actual physics. It's an estimation based on some measurements or models. So that is a very large caveat that I want to throw in there. All right. Now, what is good about statistics, and what's what is the useful element of what we're going to do today and maybe next week, is that you can use it when you don't know a whole lot to get an idea of where you should go next, what the next step might be, and that's really what it's that's what it's often used for, at least as far as I've read. When you simply do not have the data that can characterize an area, you can use a statistical analysis to get a better idea of what's going on. All right. So, moving forward. So, limited by input data analysis, often needs updated. Good usually for a first pass analysis when data is limited. Okay, cool. Right. And in the same vein, it's not necessarily an indicator of future events. It's just a guess based on what has happened there in the past. All right, because again, it's not a physical model. It's just based on what you know, this should be true. It's not based on what's there, because you're not actually measuring it, everything. That's why you're using a statistical model. Okay, so let's do this. How do I say this? Okay, so say that we have, so say that we know enough about an area that we can tell what the potential reservoir structure is like. So we have some idea of the porosity, say, at a whole bunch of different, we have an idea of the reservoir structure for a whole bunch of different test wells, or at least, at a whole bunch of different points. We haven't drilled a test well yet. We've just done some seismic analysis. And say, what was the R in here? Right. And we have some idea of the saturation as well different potential reservoirs. And I should say the oil saturation of these potential reservoirs. If we, if we've done a, if we've done this, if we've done enough initial work to get these numbers, we can start crunching some probabilities and can say that maybe 23 of the 45 wells have a porosity greater than 20%, right? And then we also, and we also know with that, hang on, I want to make sure I'm doing this right. We also know that 30, we also know that 11 of those 23 wells have an oil saturation greater than 40%. The other 12 have an oil saturation less than 20%. Right? So now the question that we want to be able to ask is what is the probability if we were just looking at a map of a particular area that happens to have that we happen to get this data from these 45 different points, say. Now a question that we want to ask is, okay, what is the chance of not only getting the getting the reservoir that has a higher porosity, but one that has also a higher oil saturation, and what's the probability of going in the other direction too? And this is the start of what are called tree diagrams. So, my goodness. Make sure I'm here. There we go. Okay, so a tree diagram more or less describes the different it's called different events and the probability of each event occurring. So the first event is we're looking for porosity. Then we're looking at oil saturation. Okay, so if the porosity is greater than 20%, we'll go on this one branch. We know that branch has a 23/45 chance of occurring based on the data that we've taken. Make sense to everyone? Okay, cool. Conversely, you can say I can say that the opposite is true for the other branch. All right. Next, I want to ask about oil saturation. Know that we have one branch with this probability. You can have as many branches as you want. I just only wrote in 2. Another branch with another probability that's assigned to it. In the same way that we started multiplying dice, the probability of different dice together, we can kind of follow the tree and figure out the probability of multiple events occurring at the same time. So say that I come into the tree, say, okay, porosity greater than 20%, and I want an oil saturation greater than 40%. Well, I have one probability here, one probability here. If I'm looking at these two occurring at the same time, that probability would be the product of all the probabilities along that that kind of walk through the tree diagram. So if I branched even further and I had additional paths and probabilities, all that needs to do in order to find the probability of occurring, of getting to this end of the tree, is just go back up along all of the branches necessary to get there and multiply the probability of each event occurring along that path. Does this make sense to folks? Cool. All right. So that's a tree diagram. However, there's another way of looking at this that can sometimes be more useful, especially when we're starting to, especially when we're trying to think about, especially when we're trying to compare of events. And this is looking at what's called joint and marginal probabilities. So let's go back to what we were doing with certain kinds of reservoir structure and porosity. This again, just from some preliminary sweep of a preliminary data gathering expedition that's gotten some information that may or may not, that does not have a lot of definition yet. So call this porosity greater than 10%, porosity less than equal to 10%, and we'll say, and to use a little bit more straightforward terminology. There's some areas have been found that where the reservoir is more or less dry, or it's not commercializable, and some areas that were found commercializable. All right. All right. So say there were 23 points that were dry, but had, even though they had a relatively high porosity per se, 35 that were commercializable and had a higher porosity, 7 that had low porosity but were still commercializable, and 25 that were both dry and had a porosity that was relatively low. All right. So what would be useful here is if we could, like I was just saying with the tree diagrams, start to get an idea of how often these different joint events, meaning two events occurring at the same time, occur relative to one another within some data gathering area. So say that all these points were taken from some space. He said that I'm looking at commercializing, and I want to compare multiple areas together. This would be one way of developing some means of comparing between those two spaces. So how to go about this? Well, how do I say this? Okay, so one way that I can kind of just look at it is just by adding up all of my rows and columns, right? So you could say, well, there are 48 dry wells here. There are 42 commercializable wells here. There are 32 wells with low porosity. There are 58 wells with, or sorry, they're not wells. 58 data points that have a higher porosity, right? But that what's called, and that kind of can give, what's called, and that kind of can give me some raw numbers, but it's not giving me a feel for what's going on. So what we're going to do is start normalizing things. So if my question is how, it's called, what's the probability of getting a drier well that has a high porosity here? I can kind of go back to my definition of which called probability, and say the number of desired outcomes divided by number of total outcomes. The number of desired outcomes, or in this case, number of outcomes that I want to know about, is 23. The total number of outcomes are 90. Cool. So you add, which is just the total number of samples here. So if I divide all these things by 90, I get what?
Numbers.
Yes, you get numbers. You get decimal numbers, as a matter of fact. You can get that too, but what are they? No, what's the number?
20, yeah, 25.5.
There you go.
25.5%.
Okay. Can you give me the other ones while you're at it, please?
To the right is 0.388.
Okay. What else?
Bottom left is 0.7.
And then bottom right is 7.7.
Thank you. All right. So what these are joint probabilities. Where the probability of multiple events occurring at the same time. Okay. All right, so one, two, put in definition. The probability of multiple events. Occurring simultaneously. All right. Now, that's nice. Gives us some idea of what's going on, and maybe one of these cases is exactly what we desire. However, you might also just say, heck, I just want to know how many commercializable wells there are in this area. What are the chances of me getting a commercializable reservoir? So in order to get that, what is it that we desire in here now? It's just these 42 commercializable points that we found. So we can play the same game in here. Desirable divided by total. We get a number which is
46.6.
okay. Conversely, 53.4%. Cool. And these are what are called marginal probabilities. So the joint probability is the probability of multiple events occurring simultaneously. So dry and porosity over 10%, commercializable and porosity under 10%. A marginal probability is the probability of a particular event occurring without regard for the other, or for the other variables. So in this, so in this example, you said there's a 46.6% chance of having a commercializable well. We don't care what the porosity is. Porosity could be whatever. All we care about is that it's commercializable, and that's the marginal probability that we computed here. All right, so that's a marginal probability. Another name for these joint probabilities that we found is a conditional probability, that this and this are occurring at the same time. All right. Okay. Okay. Right. While we're looking at this one other thing, because this is like the easiest thing to get caught on with statistical analysis. Are these two concepts, reservoir structure and porosity, are they related in any way?
Yes.
No.
Okay, so dual. Why yes, why no?
What was the question?
If you have a high porosity, it means there's a lot of flow volume,
Yeah.
so there's probably a lot of stuff in there.
Okay.
Or it could be empty.
Or could could be empty, Gino?
Lots of empty stuff.
It's out of the one.
Well,
Alright.
if it's empty, it's not dry.
Yeah. Well,
Well, I mean, wait, if it's empty, it's dry.
Yeah.
yes. Yeah, so there may be some physical connection between these two variables. Like, say, if you have very porous rock, maybe you have more organic matter that could have accumulated in that rock when it was first formed, which now, however many thousand years later, leads to a collection of petroleum products. Sticks there. So there could be some relationship here, and this is what do I want to say this? And this is part of the issue with statistical analysis. We're not caring about those relationships. If these two weren't connected in the slightest, if I was, for example, looking at say what's called porosity and the type of fluid that was collected in this place, be it gas, oil, water, whatever, there wouldn't really be any sort of a meaningful relationship there. Would that matter insofar as the statistical analysis? Not really. I'd still get numbers out. Maybe I could even use them to guide some decisions or such, like because there happens to be some non-physical relationship between these variables, be it say there was a lake here thousands of years ago, and that's led to a concentration of water in a particular place. I don't know, but the point is that the statistical analysis doesn't care about whether or not there is a relationship. So it can pick up trends and such that may or may not may not be realizable or predictable at any other way. At the same time, changes in one variable might affect changes in the other because there actually is an underlying trend. There actually is an underlying physical relationship, and that's what you have to be kind of careful about. All right, so statistical analysis isn't all just manipulating numbers. That's actually understanding where your data is coming from, okay, and what it means. So this is why you're in a rock properties class. Okay, cool. So the last thing that we're doing today, and this is actually moving a lot faster than I thought, so when we talk about tree diagrams, the probability that we're assigning to each branch, it's all really just based on what that branch represents. For example, here we have porosity greater than 20%, or saturation greater than blah. If we decide to say take this data, which is called this data here, we want to just say, okay, I want to look at whether I have a well that's dry or commercializable, and I want to know something about the porosity in each case. So this branch would be dry. This branch would be commercializable. What would be the probabilities I assign to each branch?
Dry and commercialized. The big ones.
The big ones.
48, 42.
Or 52.
48 for the dry.
Remember, we're assigning probabilities.
And have 90.
Yeah, 40
Okay. So let's say 53.9%, 50.4%, and 46.6%. So we're using we're using the marginal probabilities because that's the condition that we're describing. Now, next branch would be porosity greater than 10%, or porosity less than or equal to 10%. Yeah.
Is like the 58 over 90 and 32 over 90, is that a marginal probability also?
These?
No, the one on the right.
These?
Yeah, those are also right.
They are. Yes. It's the product. If I divided 58 by 90, found what each of those probabilities are. It's just a probability of having a porosity greater than 10%, irrespective of reservoir structure.
Okay.
Yep. So come back to the tree diagram here. If I'm looking at my branches here and say, okay, I have a 52.4% of having a dry well. What's the probability of getting a well that's not only dry but also less than 10%? What? Say again?
27.
Well, that's less than 10. Well, it's less than 10.
Oh, you must.
Are we doing less than or greater than?
This is greater. This branch is greater than.
Then
25.
25.5%.
Okay, where does that come from again? Sorry.
Box there.
Right there, the 22 divided by 90.
That's a top one. Don't worry about that.
This one?
Yep.
Okay, cool. How do I want to say this? So this is the probability of both being dry and less than and greater than 10%, right?
That's our result, right?
Right. We should end up with we should end up with we should end up with this number if we move through our if we move through our tree and say, okay, it's a dry well and it's greater than 10 per percent. However, right now we're just asking the question of, we have a porosity greater than 10% or less than 10%.
So now we're looking over the right side.
Yeah, we're looking at
32 out of 90.
You take the top one,
So whatever that percentage is.
Yeah, so whatever these are.
30, 35.5%.
Say again?
35.5% is less than
And this is?
1 minus that. 64.4%.
Thank you. Cool. All right. So, make sure I'm thinking of this correctly. Yeah. Yeah. So if we walk through this and multiply those together, what's the probability of arriving at this end here?
65 times 34.4%. Wow. Did you do it right?
Yeah, that's what I was just looking at. So I just got this feeling like I missed something. Oh,
Get 25%.
yeah.
Mm-hmm. Good job, Steve.
I'm sure I didn't miss anything. Ah, bother. Okay, I'm going to check this and get back and get back to you. Like I said, definitely, I must have missed something. I must have missed something, and I'm just not seeing it right now. But the idea is, yeah, but this is the idea that you want to go with. That if you have a bunch of different, if you have some sort of decision tree like this, the probability that you assign to each branch depends on, would depend on the combination of the that is it. Sorry, this would not be the marginal probability. This would be the joint probability. Sorry. Because this branch is inside of the dry decision tree. So you can so you fill out your tree based on where you are inside of some joint probability table. So like here we're starting out, we're only looking at dry wells versus commercializable wells. And then we're looking at, inside of all dry wells, what the probability is of getting a porosity greater than 10% or a porosity less than or equal to 10%. Okay, so that's how you label the probability of the different branches. And you can walk back through and multiply things out and see what your chances are of getting a particular outcome. Yes. I'm going to say this. Yes, and that's fine. because you're looking at, yeah, I'm sorry. It's because of the confluence of different events, and I'm blanking on something here. That's the final answer to that question. So I'm gonna get back to you as to what that answer is. This is how you do it, though, and I'll get the and Sean, I'll get the rationale. I'll get the rationale to you in an email later on this week. All right. My apologies about not being totally together for that. Are there any other questions, though?
So we, at the home, we just kind of go through this.
Yeah. You're kind of going through this kind of a decision process. All right. That's all I got for today then.